Hello everyone, welcome to the November JSE webinar. I'm Lee Harrell-Williams, I'm an Associate Editor for JSE. In a moment, is today's speaker. I just want to take a few seconds to remind everyone how the webinar will work. Our speaker will be talking for about 20 minutes. Then we'll have some time for questions. So please type the questions in the question box at any time during the presentation or afterwards, or you could raise your hand at the end of the presentation and I can unmute you to let you ask your question yourself. I'm very excited to present Shaun Wulff from the University of Wyoming. He's going to be talking about a paper that he co-authored in the July 2014 issue of JSE titled, "What is the probability you are Bayesian?" There you go, Shaun.
Thank you, Lee. And thanks to all of you tuning in for this webinar. I'm pleased to have this opportunity to share this work with you. I should also mention the co-author, Dr. Tim Robinson, also here at the University of Wyoming. Students in upper-level probability courses can generally recite the differences between frequentist and Bayesian inferential program paradigms. However, we found that these students often struggle using Bayesian methods when conducting data analysis. Some of these specific struggles include translating subjective belief to the specification of a prior distribution and the incorporation of uncertainty in the Bayesian inferential approach. By uncertainty, we mean that moving beyond just Bayes' theorem for events and actually working with probability distributions. So here we present a hands-on activity involving the Beta-Binomial model to help in understanding the Bayesian approach. This is not the first such class exercise. These authors, Albert and Rossman, Kern, DiPietro, they all propose class activities for looking at extending the Bayesian inferential approach to distributions as well. But here we want to look at what is the probability of you are a Bayesian. One nice thing about this question is it moves us beyond just the yes-no debate that can be somewhat contentious. This question is posed to upper-level statistical inference courses. These courses consist of advanced undergraduates and/or first-year graduate students. These students have a background in probability theory and integral calculus. These classes can contain the following types of students, and these examples will follow through for the remainder part of the talk. We might think of a student like Freddie Frequentist, whose training and background has been exclusively in frequentist-based statistics, and as such, the student has little background, low experience, low preference, and a low ability for applying Bayesian statistics. A second type of student would be Betty Bayesian, who through research or previous coursework has had exposure to Bayesian statistics and is quite fond of it. She would have a high background, high experience, a high preference, and a high ability for using Bayesian statistics. A third type of student might be Naive Ned, who has some background, some experience, but it's rather low, and there's not really a strong preference or a care about which approach at this point, and maybe this student hasn't really thought about differences or what they would actually do in practice for implementing a certain strategy for analyzing experiments. And we'll follow these student examples throughout the remainder part of the talk. So the talk is organized around these three aspects of the assignment. And we'll just introduce them here and we'll get to some more details here in just a little bit. So the problem we want to answer is this Q, the question, what is the probability you are a Bayesian? And the answer to this will be used with a Bayesian approach. And students have 2 weeks to complete the assignment. So the first part of the assignment consists of the prior specification, where we let this delta, this is a true probability you are a Bayesian. And as a random variable, this delta has a prior distribution, and we're going to use the beta distribution to characterize that prior. The second part of the assignment consists of an experiment. The experiment will be to estimate the true proportion of success for a randomly selected problem from a collection of proportion problems. The third part of the assignment will be to characterize that they'll have now an observation x, which will take the value 1 if a Bayesian approach was used in analyzing their experiment to part B, and 0 if a frequentist approach was used to analyze their experiment in part B. So here we have a single binomial trial that's used to obtain the posterior distribution for their answer to the question Q. So we'll talk about the first part of the assignment, Part A, prior specification. Again, cap delta denotes the probability that you are a Bayesian, and we're assigning a prior distribution for that cap delta from the beta family of distributions with values A and B. And so what students need to do is they need to be able to provide values of A and B that would adequately characterize their prior for their probability of being a Bayesian. So they have to justify in part 1 of this section what particular beta distribution they want to use. And usually they're expected to provide a graph that could be helpful in their discussion and in visualizing their prior distribution. It also provides summary measures for their prior distribution, including the mean, the variance, and the quantiles. So students are asked to bring in their background, their experience, their preference, their ability with the Bayesian approach and have that information to inform their prior on the probability that they're being a Bayesian. And so with the beta prior, we characterize the uncertainty through the prior probability density function, and this is part of the PDF for the beta distribution. So looking at our specific student examples, we see for prior specification, these students are looking at beta distributions, and so Freddie Frequentist with the solid line has a low probability of being Bayesian. And so we can see that with the black line. The expected value for his probability of being Bayesian is 0.1, and he has a relatively small standard deviation due to his certainty in preference and ability and background for frequentist statistics. As such, 50% of his probability falls in a narrower range. Betty Bayesian has the dashed line. She has a higher affinity, a higher probability of being Bayesian. We see that with her prior expectation of 0.75, and she has 50% of her probability falls between 0.63 and 0.91. Naive Ned has the dotted line, which is rather flat. He has no preference one way or the other for a Bayesian or frequentist paradigm, so his expected value falls at 0.5. He has the largest standard deviation, for he has the largest uncertainty of what his position might be. The second part of the assignment consists of a simple experiment. So students are asked to conduct an experiment to estimate the true proportion of success for a randomly selected problem from a collection of n proportion problems. They will be looking at these binomial situations where there's n trials, and they're looking at these trials which result in the total number of trials that result in a success. We have a collection of proportion problems, and students will be, in part 1 of this section, will be drawing a random number to select a problem for which to analyze. The reason behind that is that they might have information that they might bear on the problem, or they might not have information that they want to include into a particular problem. So they do need to explain any experience that they have with that particular problem that may or may not be incorporated. In part 2, they should carefully explain whether or not they use a frequentist or Bayesian inferential approach in part 1, and we'll talk about some Bayesian characterizations that they can use in their discussion here. In part 3, they briefly describe how they obtained the sample data, and in part 4, they provide summaries for their particular analysis, their point estimate, their uncertainty of the point estimate, and a 95% interval estimate for the probability of success. So with the simple experiment, what they're doing is they're looking at the current behavior, and they're bringing that to bear on their probability of being Bayesian. Okay, and again, we have this collection of n binomial problems, and in our collection we have different kinds of problems here. They could involve tossing objects or survey questions or identifications, and so again, some of these students might have some information that they do want to include in a Bayesian approach. The Bayesian characterizations that we talk about in our class the first is that the parameter of the population model is treated as a random variable. The frequentist counterpart is that the parameter is treated as an unknown fixed constant. The second characterization is that a prior distribution is used for the parameter. The frequentist counterpart is that there is no prior distribution for the parameter. The third part is that the inferential procedure is based upon the experimental outcome, whereas the frequentist counterpart is that the inferential procedure is based upon hypothetical realizations of the experiment which could have occurred. So returning to our student examples, frequentist Fred, he drew the problem of assessing the probability that a thumbtack lands point up. Since it was easy to have a large number of trials here, he used a large sample frequentist approach, and through that his sampling distribution was normal. And then conducting his experiment with 50 trials, we see down below, 24 of those were successes. He used a maximum likelihood estimate to get an estimate of 0.48 and the uncertainty of 0.071, and used a large sample normal-based interval to come up with his 95% large sample confidence interval. Beta-Binomial drew the problem of assessing the probability that a local resident has children. Betty had some information in her area where she lives about the folks that might have children, and she used a Bayesian approach. She specified a beta prior. Using the binomial distribution, she updated that to get a beta posterior distribution. So we see below that she had 10 trials. Four of those folks had children, and she used the posterior mean for her estimate and the posterior standard deviation for her measure of uncertainty, and she had a confidence interval, a Bayesian confidence interval, from 0.414 to 0.602. Naive Ned assessed the probability that a person in a moving vehicle is talking on a cell phone. He used an exact frequentist approach based on the binomial distribution. His sample size was 20. He observed 4 successes. He used a method of moments estimate, and he got 0.2 for his estimate. His uncertainty based on the plug-in estimate for the standard deviation from the binomial, and he used an exact interval based on the Klopper-Pearson approach. Okay. So part C of the assignment is to come up with a posterior distribution. So for their scenario, students are to take X to be 1 if a Bayesian approach was used in B, and 0 if a frequentist approach was used in part B. Then based on this single trial, they have a binomial distribution they're sampling from, and their posterior is obtained from their prior distribution in part A, and the observed value of X they receive from part B. So in the first part of C, they're to give the posterior distribution based on that observed value of X, and to summarize what is the mean, the variance, and the quantiles of that posterior distribution. They are to provide a plot of the posterior distribution for delta Q. In part 3, they were to describe the change that was observed between the prior and posterior distributions. And part 4, they give the ultimate answer to Q. Okay. And they should be including in their answer the posterior estimate and the posterior uncertainty for their answer. So for the posterior distribution, this is the combination of both the prior information, which comes from their background, their experience, their preference, and their ability, as well as their current behavior from the experiment where they chose to analyze their problem either from a frequentist or a Bayesian perspective. So the posterior is bringing together all of this information. So we start with a prior distribution from the beta family. Our likelihood is from using a binomial distribution with a single trial. And the posterior is the update, or the combination of those two. We come up with a beta distribution with those values of A and B for that beta distribution, and those are the probability density functions on the lower row. So for our student examples, we present here on the left side, we see the prior in the plot. On the right side, we see the posterior distribution in the plot. Down below in the table, we see the summaries from the prior on the left and the summaries from the posterior on the right. So starting with Freddie Frequentist, he has the solid line, and Freddie Frequentist had a low probability of being Bayesian. And his experiment, he used a frequentist approach. And so his probability of being Bayesian decreased as a result of the experiment. And it decreased slightly from 0.10 to 0.09. His standard deviation also decreases slightly. And we can see how the 50% of his probability moves a little bit to the left. Beta-Bayesian had a prior probability that was higher, the probability of being Bayesian. And since she used a Bayesian approach in her experiment, we see that the expected value for her, or the probability of her being Bayesian, increased from 0.75 to 0.8 as a result of the experiment. Her standard deviation decreases with that additional information. And we see how her posterior interval moves to the right. Naive Ned, he was indifferent about the frequentist or Bayesian approach, so we see how his prior estimate of 0.5 changes and drops as a result of him using a frequentist approach in his experiment, drops to 0.33. His standard deviation decreases, and we see how his interval moves to the left. Now, comparing these three, we see that the biggest change from prior to posterior is through Naive Ned, who didn't have as much prior information. So the result of the experiment played a larger role for him than it did for the other two students. So some conclusions from using this exercise. Some of the challenges that have arisen from using this experiment is that students typically struggle with correctly justifying their prior distribution. We discussed rules in class for how to select the values for A and B in the beta prior, but we have found that it really helps for students to be looking at plots as well and looking at multiple plots when trying to select a prior that matches their intent. And this certainly is one of the goals of the assignment, was to help them to address this challenge. And so discussing those kinds of strategies is quite helpful in getting the students to justify the prior distribution that they intended. A second challenge is in part B is explaining which type of inferential approach was used to analyze the experiment. And we have found that using the Bayesian characterizations or their frequentist counterparts, discussing those a bit in class helps the students be able to explain or give a better justification for what inferential approach that they used when it comes to analyzing their experiment. The most common question we get about the assignment is, what sample size should I select for my experiment? For our lower level courses, we oftentimes would specify a particular sample size and tell students to use 15 to 20 samples, what might be convenient for them. For our advanced levels courses, we ask students to think a little bit more about sample size. It plays a very important role, not only even in terms of the inferential approach that's used. So we might ask students, for example, to specify a sample size that gives them such an uncertainty estimate, or gives them such a size for a interval, whether it's a Bayesian interval or a frequentist type interval. Sample size also affects the role that the prior information plays, so it is an important thing to consider and to think through when it comes to analyzing the experiment. And of course, a challenge is the last part, and the final question is the ultimate answer to the question, what is the probability of your Bayesian? What has helped, we think, with students to answer that question is to separate the assignment into these pieces of parts A and B, and then C is the ultimate point at which they combine all that information to come up with their answer to Q. That answer to Q is the posterior mean, and their uncertainty comes through from the posterior standard deviation, and they also use these percentile intervals, or we could do something more fancy with credible intervals to give some understanding of the uncertainty that's involved in their answer to the question of the probability of being Bayesian. Our assessment of the assignment is we have found that the assignment helps to maintain these distinctions between frequentist and Bayesian approaches. As a result of the assignment, we feel that students do a better job being able to separate and to distinguish these approaches. Oftentimes the assignment is given when we first introduce the Bayesian approach. Often this occurs in point estimation. So when we move on through the course and talk about other Bayesian topics like hypothesis testing or interval estimation or prediction, we have found that as a result of the assignment that we can have deeper discussions about some of the issues involved in doing an analysis, such as the choice of the prior, such as the interpretation of the results. And these issues are quite important, and it's also important to point these out to the students because the assignment can be a lot of work for them. And so when we come up to these later topics, we kind of like to refer back to the assignment so they can see how we're using that information and the things that were learned from it. Students ultimately we have found, can do the machinery, the calculations that's required for the Bayesian approach. The ultimate concern was that the ability to do it and use it in practice. And so we have found the largest benefit comes to those students who have limited background in Bayesian statistics, because this provides an opportunity to carry out a Bayesian analysis. Even if it's really simple, it allows them to carry out one themselves and to have to provide the interpretation of it. And so we have found that to be probably the most rewarding aspect of using the assignment. All right, thanks. I'll turn it back over to you.
Okay, thank you. We do have a couple of questions that have popped up. The first one is, could you explain the reasoning why you're using the beta distribution for the prior?
Yeah. In one sense, the beta distribution is convenient for carrying out the calculations. It's a member of the conjugate family, so for a proportion, the beta prior distribution has a support from 0 to 1. So for modeling a probability, it's quite convenient. The beta distribution also has a number of shapes that can be used, so it's very flexible for incorporating prior information. On this slide, we just see a couple of examples of the beta prior, but we can have all kinds of shapes. And so it's quite flexible in incorporating prior information. For courses that are more computationally geared, there's no limitation that it have to be the beta prior distribution. It could be other kinds of distributions for which results are not that tractable. But here the results are exact and they're easy to do. And so at this point, our concern was not so much to stress computation as it was to work on interpretation and understanding of the Bayesian approach.
Okay, that's a great rationale. Thank you. We've also been asked, do you have examples like this for questions where you're looking at confidence intervals or Bayesian credible sets?
Yes, and that's a good question. Credible intervals, Bayesian intervals, or percentile intervals, all of that is really good for having students understand uncertainty and uncertainty in the Bayesian approach. In our examples here, in particular, Betty was using a credible interval in her results, and that's what was presented here, was the credible interval. In the student summaries for the posterior distributions on this slide, these are percentile intervals, and either one. But yeah, we look at credible intervals. We can program some of these for our advanced classes. Otherwise, for our lower level courses, we would probably use percentile intervals for them.
Okay, and you mentioned lower level courses there. That was one of the questions that was posed, was have you tried this exercise in an introductory stats course?
No, we have not. These formulas are rather straightforward to use. We oftentimes want to show the students the integrations involved. If that's not a requirement, I think some of this could be done in an introductory course. So I think there are some possibilities there. Some of these formulas could be coded up for students just to plug into, and this could be a useful exercise for students at that level.
Okay, and then our last question for the moment is, when you were talking about the activities that each of the students did, Frequentist Fred had done the Frequentist approach, and so have you talked, do you talk about in the class or after at the conclusion of their exercise about what would have happened had Frequentist Fred had a Bayesian, had been assigned to do a Bayesian analysis, or if naive Ned had been assigned to do a Frequentist analysis instead of a Bayesian analysis? So what changing up that type of experiment that they did, and so in essence that what X equals when you're updating, do you have discussions about that in your class?
That's an excellent point, and I appreciate that question, in that we do have discussions about the assignment after it has been finished, and we go back to the priors. We go back to the posterior distributions. And that kind of helps students to know where each other students are in the course and their levels of interest and their behaviors. That particular suggestion, however, would be a valuable one. That's not one we often do, and that is a great idea of something we probably should incorporate to let students know and see how students maybe not operating in what we might expect them to do, how that might affect their results. And even though based on a single trial, some results may not change a lot, it certainly can help the students' understanding to see that and to see how things would operate differently. So I think that's a great suggestion.
Okay, do we have any other questions from the audience? Anyone want to raise their hand? No? Okay. Well, I'd like to thank you all for attending. This is our last webinar for the year, and we'll start again next in 2015 with some other articles from recent JSE issues. On your way out of the webinar, please take a moment and leave us some feedback about how we're doing, things we could do to improve your experience, or potentially even papers that you've read in JSE that you'd like to see